So the purpose of my presentation is kind of twofold. Firstly, I want to introduce you my team members, because as I have mentioned many times, the purpose of this school is networking, and I want to also integrate my group into you and into your groups. So firstly, I will briefly tell you about my team members, what they are doing. There will be contacts, you may contact them. Probably you know our website, so this is the website where the MRS school web is. So if you go there, you can find also like all the people and their contacts. So feel free to send them email or find them here. Most of them are here this week, so feel free to speak with them. And the second purpose of this talk is to show you what we are doing and to give you some knowledge on deployment of multi-robot system in real environment in wild. So let's start. So this is the team I have established 7 years ago with 2 of my colleagues. The group is growing a lot. So as you can see, now we are 40 people, and we are still hiring. So if you would like to join us, it would be great. Just let me know. We have some postdoc positions, associate professor position open, and also a PhD position. Or even we have a lot of master students, so if you would like to study master in Prague, it's also possible. Here you can see a Hall of Fame of our group. I will show you more details about these competitions in my talk, so I don't have to do it right now. And let me start with the people. So Petr Stepan, he is the one of 2 he was establishing the group with me 7 years ago. He is working mainly on mapping, using LiDARs, sonars for mapping of the environment and object detection. Vojtech, the second most senior, I would say. He is working on motion planning, so all these problems, like even molecule of proteins planning and so on, but also planning for drones and multi-robot systems. So he is also here this week, so contact him if you like his topics. He is mainly working on RRT algorithms for planning. Tomas, Baca, you will meet him for sure, because he is like one of the core members. He is coming right now. One of the core members of my group. He designed the main components of the MRS system you will be using here in this summer school. He will give you some lecture today afternoon how to use the system. And also he is working on several interesting topics, including even satellites, CubeSats. He designed some system for that. Motion tracking, trajectory generation, MPC control. Also, he's leading a project on radiation localization and mapping. I will show you a little bit later. Robert Pienička is our new postdoc. He's coming from Davide Scaramuza lab in University of Zurich. He was doing PhD with us before his stay with Davide. His main interest is planning, kind of like traveling salesman problem planning and orienteering problem, and this kind of applications. Now because he is coming from Davide's group, he is going to apply vision into multi-robot systems. Another postdoc, Vojtech Spurny, is mainly working on high-level planning, system integration. He is our expert on communication, like how to really communicate in the real world. Tiago Nascimento, an assistant professor within my group. He is working on formation flying mainly now, and model predictive control, even non-linear one. now he's leading a marine robotic project in my group, so I will also show you a little bit later about the newest results we have achieved in this project. Daniel Bonilla, our expert on communication. He has a theoretical background in communication, so he is designing methods for communications aware trajectory planning for UAVs. Viktor Walter, he designed quite unique smart sensor UVDAR, which we are using for swarming. I will describe you what UVDAR is a bit later, and you will have opportunity to meet Viktor and discuss with him this unique sensor. Maybe it could be useful for your research as well. Matouš Vrba, my other PhD student, he's working mainly on visual detection of flying targets in the proximity of the drones. He is our main kind of leader of a drone hunter project. I will also explain you a bit later. Matej Petrlik, he was leading our team for DARPA subterranean challenge, which I will also present you. So his expertise is on state estimation for UAVs, localization and mapping, multimodal onboard sensor fusion, and these subjects. Pavel Petracek, he was also working for DARPA SubT, and he is kind of leading a project on scanning of historical buildings. I will show you some results later on. So his topics are UAV localization in perception degraded environments. With Kratky is cooperating with Pavel on the historical building scanning. He's also one of the biggest experts on formation flying and stabilization. He has achieved a lot of interesting results in these fields. Petr Stimminger, another PhD student of mine, is working on perception-driven autonomy for mobile robots in hazardous environments. He's focused on using radiation detectors on drones. So it's a quite interesting project on source of radiation localization. I will also present you a bit later. Another PhD student of mine, Jiri Horyna, he is doing a really interesting thing on swarming in desert environment where you don't have enough visual features, and we are interested in applying robots without GPS there, with using vision only. And you can imagine that if you are flying above dunes and sand in desert, it's quite challenging task to be not lost and to be integrated and be able to fly in a swarm. So if you are interested, contact him. Vaclav Pritzl is also my PhD student working on cooperative navigation of heterogeneous UAVs for inspection of indoor environment. So the idea is to have multiple UAVs, one big guy, primary UAV in the picture, which is carrying, which is well equipped with sensors, and the other guys around are maybe like just with camera following this guy, but they are much smaller, so they can explore smaller environments around the big robot and then return back and maybe even land on the big vehicle, which is a topic we are working on right now. Parag, he's quite fresh PhD student. He started this year, and he has already achieved excellent results on landing on boat in waves. I will show you as well if I will get some time for that. He's working on model predictive control and also nonlinear model predictive control, state estimation and prediction for tracking of marine vehicles. So it's quite interesting application from offshore. Akash is starting like in few weeks towards PhD, but he has achieved already interesting results on human-swarm interaction, controlling swarms by gestures. So in case you would like this topic, he's also here. Okay, so these were researchers, I would say, but we have also a strong support from engineers. We have a team of hardware engineers, so they are preparing drones for our PhD students. So it's kind of approach I like, that the students, the PhD students, they have really 100% of their time for research and programming, and they don't have to spend a lot of time with hardware preparation. So it's working like that in our group, that if a PhD student wants to do some experiments, he'll just sending description of drones, a number of drones to these guys, and they will prepare the fleet for them. So this is why we are able to do even 20 UAVs experiments. So, because these guys are really good. They are managing also the hardware, like kind of design of the system. They are able to add different sensors, as you can see here in this picture, and the details you can find in our fresh publication in IQAS, where the hardware platform is described. So this is the first paper we wrote just about hardware. So if you are interested in like finding out what our hardware is about, read that paper. This is our software support, I would say. We have also a lot of software engineers. Some applications like require programming, but not doing research. And again, I want to protect my PhD students from doing like programming for companies. So we have these guys for doing the first line, kind of, for programming, for application-oriented projects, writing GUIs and so on, and PhD students are just providing the scientific results these guys are integrating. We have even technology transfer. That's why I put it there also. Two colleagues, they are working on the edge between my group and a company, Fly for Future, which is kind of organizing this event. So their task is kind of to take the technology we are developing at the faculty and try to sell it or to put it into business. And of course, our administration support and PR support is also very important. So this is how my group looks like. So if you would like to speak to any of these guys, just find their name on the webpage we have. And also all the projects I'm going to present to you are well documented on the webpage. So browse it, take a look, contact the people, they are usually contacts. And also we will put the PDF of my presentation like online as soon as possible, right, Honza? So the students can find contacts or papers there. So now let me start with the second part, describing our research. First, let me start about swarming. So maybe it's good that Hannibal is not here anymore, because I will show you some swarming experiment with 4 drones. Because it's not so easy, you know, to deploy, to start with 20 drones in forest, for example. Hannibal is here. Ay, 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 ay. So the first video there is a swarm of 4 drones in artificial forest. No, I'm just kidding. Of course, you have to start from a smaller number to test the basics, and then continue with large swarms. So what's our main motivation? As I have mentioned during Hannibal's talk, at the end of the talk, Okay, thank you. Now, really, thank you for coming, and see you soon. And okay, so the motivation of our research is to be able to have some technology which is applicable for cooperating robots which are sharing the environment without GPS. So in situations where there is GPS jamming, imagine that you have 100 drones flying around your building, and some kid can buy a GPS jammer for $1,000 or even less dollar in eBay. So, and it is a lot of fun to switch off GPS, right? So in that case, the drones must be prepared for the situation. So we have to design a technology which will allow at least some degraded functionality of this swarm, just to survive, just to fly together somewhere safely home or something like that. So we need sense and avoid, right? We need to sense other drones, even if they are not communicating the position. We need to send them if they have to share the common space. We have to fly without GPS. We have to be prepared for a situation where the communication is jammed. It's so easy to jam communication, right? And even if there is no communication jamming, we have experience from the real world, and it's so easy to find a situation where the communication is not working at all. And for real-time control, you need 30, 50 hertz sending the messages with current communication. Not reliable at all. If you want to send a lot of data, it's not reliable. So we are focusing on strictly decentralized systems with onboard computational power and sensors. So all drones, in fact, you will see here in my presentations, are done. I don't know what's happening with this. Are really like smart agents which are acting in an environment together with their colleagues around. And we want to go, as Anibal mentioned, to scalability and large systems, of course. So even if I'm presenting you videos with 4, 5, later 10, and at the end 20 drones, we want to go to hundreds. And all the tests in simulations are usually done with this amount of drones, but we have only 5 hardware guys, so they can't prepare for each of our PhD students 1,000 drones so far. But we are growing up. And we are interested in environment with high density of obstacles, because usually this is the place where GPS is not working, and this is the place where communication is not working. So like being in caves, being in underground, being in urban, being in forest. To solve this problem, we had to achieve several scientific achievements, I would say. You have to have very precise state estimation and we have found that if you want to have a reliable system, you have to have multiple sensors. So that's why our MRS system is designed for fusing multiple sources of information for a single measured value. So we are usually combining multiple ways how to estimate height of the drone above the floor, because in different conditions you may have troubles with these sensors or with the other. The same with lateral localization, the same with sometimes we combine vision, LiDARs. It is necessary if you have to have industrial reliability. So for example, these pictures on the top, they are from tunnels here in Prague for motorway, and they wouldn't allow us to fly there without reliable system. And the same is with the churches you will see later on. You have to have very precise control. So our approach was the first where we were able to control the drone with MPC on board out of the laboratory conditions. So we have published 5 years ago first paper on this topic. Of course, now you have new techniques, you have nonlinear MPC, everything is even more precise, so it's continuing, but this is important. You have to do obstacle avoidance and mainly detection, and again, usually we combine multiple sensors to do that, 3D cameras, LiDARs, single monocular cameras. There is a lot of technique, as you know, and we try to combine all of them together. So this is the system control architecture of the MRS UAV system. I will skip this because Tomas Baca will tell you much more details, and he is expert on that. This is the important publication. If you have time, please read it or just go through. There are the important and useful information for you. And of course, if you will be using our system in your research, please cite it. The core of the MRS system is this sensor fusion, as I have mentioned. Let me also skip it for now. And the same with state estimation and control part. Just some commercial, as I have mentioned, the Fly for Future. So they have designed now such a web where you can really select a proper system, proper drone for your research development with our system. So if you would like our system after this summer school, you can even buy a drone from the company. You can start immediately doing experiments. From the last summer schools, there was like 5–10% of students buying really the system, because it's of course useful to be able to immediately start research and experimenting without having these 5 guys behind you. Okay, so let me introduce you also the UVDAR. So I have mentioned that Viktor Walter has designed quite unique system for swarming. So this is again following our intention to have fully decentralized swarming without any, or multi-robot systems if you want, without any communication. So if you want to fly with your friendly UAVs together, you need to observe them if you are not allowed to communicate. Viktor was thinking about using vision, because cameras are lightweight, they are quite powerful, but in real world situations, light conditions are bottleneck. So if you have to fly inside of a building from outdoor, if you have to fly in cave, illumination is always a problem. So we have found that using active markers is a way how to achieve reliable swarming for now. Maybe in future, in 10 years, there will be some technology without using, like for example, these event-based cameras, as it was mentioned by Anibal, which is a very promising technique. But for now, probably this is the only solution how to achieve 10–20 UAVs swarms flying in close proximity without any communication. We are using UV because, as you can see in the solar radiation spectrum, that in the UV part of the spectrum there is drop down. The thing is because of atmosphere, right? Everybody knows it. Sun is like the sun. The radiation from sun is filtered out by atmosphere in this UV spectrum, so that's why we are using UV LEDs mounted on our drones. So this is the picture, this black picture. In fact, even that picture, you know, it would be very difficult for you to find in this RGB picture, the top one, the drone. It's somewhere hidden in front of the cars. But in the UV spectrum, you will see these small dots. And this is the information you need. So it's very simple to threshold this picture to get the bright spots only. There will be only UV, only the LEDs from our drones, because there is usually no other source of UV radiation in the nature. If there is, for example, some reflection, we are using a trick. We are blinking the LEDs with a given frequency, which allows us to distinguish between these very rare sources of UV, like reflection of sun, for example, or the sun itself. Sorry, but I have to take my beer. And there is another advantage of blinking. You can change the frequency of blinking, and by changing this frequency, you can communicate. So we have designed even a method for communicating by the blinking of LEDs. So the drones can send a simple command like, now, let's follow me, I am your leader, or let's land, it's danger now, or you know, such a simple command we can communicate. We are also using possibility of signal propagation. So for example, a drone will see some kind of predator, some dynamic object coming we want to avoid. So using this blinking, this information can be spread into the swarm. Now go out of this danger object immediately. And we have shown in both in theory and in real experiments, then such a signal propagation is then much faster and it's safer, and the drones can really escape fast from even fast coming object. So here you can see that you don't see almost anything, which is good, because these are cameras from all the drones. So each drone is equipped now with 4 cameras to all directions. There is a filter which allows only UV spectrum to go to the chip of the cameras. So you will see only black picture with bright spots of LEDs mounted on other robots. And here in this experiment of flying through the forest, each of the drone were like estimating its position by SLAM from LiDARs, but these maps are not shared. There is no communication at all. So each drone is a single agent acting in the environment, avoiding the trees, being localized by the trees, and just observing the others and being localized and stabilized within the swarm. So now, because of Annibal, I edit a video with 20 drones. So our record so far is 25. We are doing, sorry for the Czech video, I really did it now, so I was not able to find the English version. But it's about swarming in forest. And we are here using also UVDAR to stabilize the drones. So the partner we are cooperating in this project, they really don't want any communication, any GPS. So the drones here are using GPS, but they don't communicate. They just observe each other. So this video is with 10 drones. Yes, 10 drones. Then later on there will be 20, but there is not much big difference between the behavior. So we have already shown the scalability even. Okay, let me continue with the second main focus, research focus on my dream, which is inspection of indoor space by multiple robots. Our key project, I would say, is a project on inspection of historical monuments. I like that project because we are cooperating with historians, so there is really like cooperation with people out of our field, and we are visiting the most beautiful cathedrals and castles in the country and the countries around us. So it's a lot of fun there. The motivation of using drones indoor is obvious. We are able to get the same information. For example, here, by some coincidence, this picture I found at the like Google is from the same church as we were flying. So I asked the people, and they spent their 4 months with building the scaffolding, doing the job, making pictures, and we did it in 1 day with a very similar quality. Even sometimes we got much better pictures because it's difficult to make a picture without this infrastructure there, right? Without the scaffolding. So with drones, you have more flexibility. You can do it much faster. You can imagine the advantages. It's cheaper. Maybe I will skip this. Even the video was stopped. I don't know why. So I will skip this picture. I just wanted to show you here that we have scanned already 15 objects in Czech Republic, even including UNESCO objects, which again gives you some evidence that the system must be really robust if we are allowed to go to such a expensive, historically expensive, but also really expensive buildings and rooms. I don't know why the videos are stopping, but this is also not so important. Here you would see how the map is being created, how the 3D model is made by the drone. Maybe with this slide, I will a little bit describe you how the process is going. We are scanning the churches. So at the beginning, we are using a terrestrial ground scanner, a 3D scanner. We could do the job without pre-scanning the environment. We are able to fly into completely unknown environment and do kind of 3D LiDAR slam. But because of the reliability, we take the opportunity that we can come to the church day before, we scan it by a 3D scanner, obtain a 3D model like that. Then we use a 3D model even with pictures, like colored one, which is on the picture above. And this 3D model is used for the client, which is historians or owner of the object, to tell us where we have to take the picture, because we don't know what they want. So they really can play with this 3D model. They can put the camera into the 3D model virtually, check what will be the result. So they can even like see a low quality picture taken from ground by this 3D scanner. And if they are satisfied, they just save the position. And we know the position of the drone that must be visited with orientation of the camera. So we will get a set of these positions. We plan some simple TSP, traveling salesman problem algorithm, to visit these locations. Then we smooth it by trajectory planning. We can check if the result is safe. Even usually we have to show it to the client, the owner of the church. Sometimes they tell us, no, please don't fly there. This painting is really like the most expensive here, and avoid that. So we just a little bit change the plan. If it's approved, we just come there, put the drone on the ground, start button. The drone will make the pictures and return back, which is a big advantage because we have to close the church or the castle or whatever only for the few minutes of the flight. Then we go out immediately, take a look on the picture, check with the client if it's okay, and if yes, we are satisfied. If no, we do another mission. So we will occupy the objects in the minimum possible time. So let's hope that this video will be running. Yes. So I will show you some pictures from this scanning. Unfortunately, it's not so well visible. We try to close the screens, but we want to also provide you some air. But this is a compromise we have. Yeah. Unfortunately, we cannot use air condition here because it's historical room. So we try to get some mobile air condition for you, but it was not allowed. So if there will be even more hot days like tomorrow and the day after tomorrow, it may be painful. But anyway, so here you can see even two drones flying in the church. On the next slide, I will show you why. So here you can see that how the drones look like. You will see the drone during your lab tour tomorrow or the day after tomorrow. This is how the 3D model is created. I forgot to mention one interesting thing, that if you are doing the scan from ground, there are some occlusion usually. So there are some places where you cannot scan from the ground, and the drone is using 3D LiDAR as well. As you can see, we are using Oster. And the system is able to add the missing information into the 3D model by the drone. So this is the thing. So this is how the drone see the environment, the church. And this information is used for localization of the drone, for planning, because the plan was done within this 3D model, and also it can add the additional missing information. And now the idea of using multiple robots there. I'm leader of MRS group, and this is MRS Summer School, so I have to put there multi-robot, right? So we found an application which is interesting. To say true, we are using this technique only like in 1% of photographs we are obtaining in the church, but it's mainly a lot of fun having their multiple drones. So the idea behind is, here you can see two pictures. They were both taken by a drone, by the same drone. And here the light was on the same drone as the camera. And here the light was from side a little bit on another drone flying in a formation. You can see that here you can like see much more details, you can see the depth. And even they are using a technique, like real historians are using, they are playing with light and helping them. So they put a light very close to wall, pointing from side. Then they make a picture of a wall, and they can see even like a small bubbles, you know, by humidity, for example. So they use this for quite a powerful source of information for inspection. So we have decided to do the same. So we have formulated our formation flying approach to satisfy the constraints of this application. Of course, the drone cannot be in the field of view of the main drone. Then it should be in the sufficient distance because there is a limited source of light. So all these constraints are included into optimization of the controller of the formation, and it's here. So both drones are equipped with 3D lidar, so they are independently localized in the church, but they are, in this case, they are communicating their position, so they can really cooperate and fly together. Of course, you could also apply the UVDAR, but here for this particular application it was not necessary because the communication is reliable there. And we don't need to communicate too much because we in fact pre-program the trajectory. So it's not, I mean, they would not collide. So there is some bumper, but the drones are not able to be really autonomous. So they are kind of following pre-programmed trajectory, which is necessary because of the safety of the system. Plus, there is another interesting technique, which is called reflectance transformation imaging. Historians, what they do is, if they want to get a model of illumination of an object, they make a lot of pictures from the same position. So let's say here is the drone. Can you see the drone in front of the statue? So this drone is carrying a camera, and there is another drone flying with light around. So normally people do it without drones. They really move the light around and make a lot of pictures from the same position. So we have to stabilize the drone as much as possible, and then plan a trajectory for the drone with light to provide different illuminations from different positions, putting all these pictures together, obtaining a model like this, and then later on in lab, you can play with the illumination. So this is done like offline. So the historians can then study the statue from different, and again play with the light. So it can show them that there is some problem, that there is some crack, that there is some bubble which shouldn't be there. And we have done this in a real environment in church. The funny thing was that we had to do it during night and without any lights in the church, because otherwise it would be affecting your result. But we are using 3D LiDAR, so for us it worked even better than with having a lot of light there. We are also using other like frequencies of light to like multispectral cameras, and in some of them, if we are making pictures in UV, for example, we have to fly in complete darkness. So it's really scared because if we have a safety pilot, this guy cannot do anything. The drone even cannot be equipped with the small LEDs to tell where it is, because even the small LEDs would affect this UV filming. So I never want to watch this. I am always going out and just waiting if there will be crash from inside. But it never happened, to say true. In this project, we have never broken anything. Okay, let me now continue with competitions. I am quite good with timing. Let me start with the subterranean DARPA challenge I have mentioned before. So the task of this challenge was to deploy a team of robots, not only drones, but also ground robots, into completely unknown environment. So they only told us that it will be kind of a tunnel kind of environment, which means it can be a mine, for example. And since we knew where it will be deployed, we expected that it will be golden mine, for example, or coal mine. The first testing was done in Colorado. There are golden mines. Then in Pittsburgh, there are coal mines. This was the only information we got. And we were not allowed to enter the environment before the robots, even after. So they allowed us just to come close to the entrance of the system they prepared, and then send the robots there. There were problems with communication. It was real tunnels, so the robots could communicate only in straight line, like tunnels. If there was a small curve, the communication was not available. There were no lights, or sometimes there were lights, but in some places there were complete darkness, so we had to carry the light with us, as you can see the drone. And there was a lot of dust, you can imagine. So we were playing, I will play some video first. So we were, this is from the Rocky Mountains close to Denver. And yeah, so this is the entrance of the tunnel. So the tent, we could be in the tent only in front of the tunnel, and send there all the robots. The robots could be teleoperated, but there was only one guy from the team which could be interacting with the robots, and we had like 15 robots. So of course, at the end, all were fully autonomous. Sometimes the guy just could send a command like go to this area of the building if there was communication. With drones, it was fully autonomous, so there were no way to interact with the team. So here you can see some like pictures from environment with like a huge amount of dust. So we found, for example, that the RP LiDAR, 2D LiDAR we are using here, is not working at all in such condition, that you cannot rely on vision at all. So at the end, we found a special frequency of setup of Oster 3D LiDAR to survive in this environment. So this was also interesting lessons we learned how to fly in these really difficult conditions. And as was mentioned on the previous slide, we were first in this first tunnel circuit. It was split to 3 circuits. The first was tunnel, so we were first among self-funded teams, and third in total, comparing all the teams supported by DARPA. So we were really like poor guys there without any budget, and we achieved third place. So they were kind of shocked because the other teams got $2 to $5 million for participating only on this tunnel circuit. So they invited us for an urban circuit, which was an abundant nuclear power plant. So here you may see the building to fly in. So the nuclear power plant was never in operation, so it was not radioactive, but it was very similar environment as in the real power plants, or it was in fact a real power plant. Again, we were flying there fully autonomously. There was even really no way to communicate because the walls were really thick. And we deployed there a team of 3 cooperating drones and again 6-7 ground robots. We achieved again first place among the self-funded teams and again third place in total. At that time we got $500,000, which was better than before. And finally, we got even funding from DARPA, even being not from US, which is also not so often. Here you can see some pictures from the deployment in the real building. So again, as I have mentioned, the drone is carrying all the sensors, all the computational power on board. So it's building a map using a 3D SLAM technique. So it's a completely unknown environment. We couldn't know even like how the structure of the environment will be, really nothing. So the drone, the planning algorithm, this was also some contribution we did, was prepared for really large open area as well as tiny corridors, narrow corridors. So the planner was prioritized the open space, of course, and flying faster there, but it allowed also going to narrow space slower than closer to obstacles to be able to explore also the part of the environment behind this bottleneck. Usually they were some small corridors, doors, windows, and behind them there were like other space to explore. All the robots were equipped with onboard cameras to detect artifacts. So the task of the mission was to detect humans or objects of humans like cell phone. Here you can see a backpack by a camera. The robot was equipped with kind of small neural network to estimate if it's the object or not. And then the candidates objects were sent to the operator. So the operator received limited amount of pictures because of the communication problems, only few pictures with the objects. Sometimes it was only a result of the neural network without the picture itself, if it was not allowed by the communication available. And based on this information, the operator decided what object this could be, and it was reported to the organizer. The most tricky part was the fact that they required very precise position information. So even in 3D coordinates. So the robots, after traveling a few kilometers in the tunnels, had to report its own position and the position of the artifact with precision of 5 meters, which is, if you have experience with field robotics, it's quite difficult if using drones. Mainly if there are straight corridors without any landmarks on it. The cave circuit was unfortunately cancelled due to the COVID, but we did really, really nice experiments during the testing period in real caves in Czech Republic. And we established an interesting contact with speleologists there, because they are interested in exploring part of the caves which were never visited. Sometimes there is only a small, narrow entrance into some other caves, too narrow for people to go in, but we could manage to put there a small drone there and do the exploration behind to tell them if it makes sense to expand the corridor to get there or no, if it's blind. So we did a lot of testing in these caves. Ještě tak 20 minut, no. Já jsem říkal, že budu půl hodiny zpožděný proti tomu. And this is a final event. It was a combination all of these three challenges together. So it was a cave, urban, and tunnel combined together. It was done in a mega cavern in US. It's a huge cavern, cave, where they in fact built small caves, small tunnels, small metro station, as you can see here. So they really built a metro station. DARPA built a metro station to test just for this one day of flying. So it was amazing. And it was very, as you would see maybe some pictures later on, it's very in details, you know. They made all the details there. It was divided into two parts, a virtual challenge. It was done in Ross Gazebo. They made 20 really complicated environments. So we were flying in caves, tunnels again, urban. They were even like falling rocks and really difficult condition. And then there was the system track, they called it, which was a real deployment of robots. So here you can see, for example, they really made some toilets there, you know, so it was unbelievable. They made Mind there. So at the end, we were second from all together in the virtual challenge. The reason was that the virtual environment was prepared for drones. So ground robots were not so good in this kind of environment, but because it was a large open space with a lot of obstacles for the mobility of ground robots. So we achieved well in this, and also like the first 6 teams in this virtual challenge were using drones, and in particular they were using our drones. And in the system track, it was vice versa. It was prepared for ground robots. So there were only narrow corridors, long corridors. So even we managed to fly there, but the drone was lost at the end. So Kostas Alexis will tell you how it was for the ground robots there. His presentation is on Wednesday, I guess, or later on. And we managed the best probably with drones. Okay, so this was the DARPA. Now let me tell you a little bit about the MBZIRC. My presentation, yes, I have still almost 25 minutes. We are behind the schedule, so anyway. The MBZIRC competition, which was already mentioned by Annibal before, he was also competing there. It was probably the biggest competition for drones in 2017 and 20. It took place in Abu Dhabi. In 2017, there were 2 challenges for drones. One was a landing on a moving car. So here, this car I took from my father-in-law. I didn't tell him what will be the purpose of the driving. So we were really testing landing on the car, and you can imagine the first attempts, how it was. For the second challenge, it was a collecting of objects. So here, these pictures are already from the competition. They were metal discs, static, as well as moving on some small ground robots. And the drones were tasked to grasp the metal discs from the arena, to localize them and put them into a bin. We won this challenge for grasping of the objects. We did it with 3 drones cooperatively, so they were really sharing the environment, communicating if there was communication available, the task, and trying to optimize the performance. The second task was landing on a car. We were second in this challenge. Guys from China was better than us, a few seconds only, but they were really good. But we in this first MBZIRC challenge, we learned a lot. For example, we got the experience that even if communication infrastructure was prepared there, they installed Wi-Fi, they spent $100,000 to prepare Wi-Fi infrastructure there. The communication was not reliable enough. So there were places in the arena where the communication was not working well, and we have prepared the system with, as I have mentioned again, with kind of degraded performance. So if there was communication, the robot could communicate and do the maximum, optimize the task. But they were prepared for situation without communication, and in that time they were using, for example, time windows to approach the final location for the bin, to put it there, to avoid collisions. Another thing we have learned is that if you want to deploy your system in real-world conditions, you have to train in real-world conditions. So we did a lot of experiments in the desert of Abu Dhabi, near to the place of the competition. Most of the other teams prepared themselves in their laboratories, and they came to the arena and were complaining that there is a sun, that there is a wind, there is a scent in the air. So some things which are obvious if you are living in Abu Dhabi, but they couldn't imagine it, that the sun could be so strong, that there could be wind. It was on the coast, so between desert and sea there. So of course there is wind all the time. So this was probably the reason why we won this, and also this was reason why we started our strategy of having a lot of experimental campaigns in real world environment. So we really regularly, 4 times, 5 times per year, go to forest, go to field, and test our system there. So this is the only way how to really design a robust system for real world conditions. If you think that you will do it only in simulations, even if this simulation will be super realistic, and then test it in lab conditions, probably you will design something which is completely not useful for the real deployment. So this was the lessons we learned, and there is of course a lot of fun. We are going there with our team. We take a lot of beer there, and we can enjoy and kind of do networking within the team. Okay, MBZIRC 2020. So at that time, our team was already much bigger than before, also due to the money from the MBZIRC, to say true. The challenge, there were 3 challenges. At that time, we decided to compete in all of them because we wanted to try to win the competition entirely. We did. And the first challenge was to capture and neutralize intruder UAV. So the drone was the task of the drone was to catch a yellow ball which was carried by drone, so the left upper picture. The second challenge was to build a wall from bricks by drones and ground robots. It was super challenging. And the third challenge was to extinguish fire, as was mentioned by Hannibal. So Hannibal's team won the third challenge. We won the second challenge. We were second in the first challenge, and we won entirely the competition. I will show you some pictures now. Yes, so a part of the first challenge was also destroying these balloons. So this system was done by our bachelor student. He is really smart guy, probably maybe sitting somewhere here. But he did it almost alone, and he achieved one of the best performance, so that was great. The second task, catching the balloon from the flying vehicle, was really challenging. We managed to catch 2 times the balloon, or to put it out of the drone, but we were not able to really catch it. It was the reason why we were second. Again, the same Chinese guys won it. Unfortunately, they are not here because of COVID. It's really stupid. They wrote me. Maybe they are online, some of them. The second challenge was the building a wall. You could see that the drone was equipped with some gripper of the bricks, and they were placed to the wall. So we won this. And the third one was using the blankets to extinguish fires on the ground and real water for fires on the facade of the building and even inside of the building. Okay. So these were competitions, but I don't want to do the competition just for fun or for the prize money. I always want to have some technology transfer out of these competitions. And we achieved that in both of these, in fact, and also in the DARPA. I will give you some examples. So for example, this is a drone we are designing for a client from, in fact, Czech Republic, but it's an international company. They want to fight with fire using these capsules. So these firefighting grenades are equipped with a special liquid. In contact with fire, it makes a foam and it removes air. So if you use 5 of these capsules, you should distinguish a fire in a regular flat. So they want to shoot these grenades from a drone through broken window. So this is their strategy. So for that, we have designed already first prototype, so the drone on the right upper corner, to extinguish or to test that it's doable and that the grenade can be really put it there. We did some testing with real firefighters, like a brigade here you can see pictures from this mission. So the firefighters came with our drone. They pretended that they will use it. Of course, we used it at the end. Then the drone autonomously found the window using thermal camera, was oriented in the way that it's pointed to the window. So we of course tested how to get the grenade into the place. So here you can see some pictures from the onboard thermal camera, and we could quite precisely shoot the grenades into the fire. Now, maybe, I'm not sure, I may try to ask my guys, during the lab tour you could see a real scale drone. The real scale drone is of this size, like from here to the wall. So it's a huge drone to carry 6 of these grenades, because as I mentioned, you need 5 for a normal flat, so they want to have 6. So it's going to be a huge drone, and we have already a contract with firefighters in Pilsen, which is the 4th biggest city here in Prague. Pilsen is kind of smart city, so they test all the technology available. So we will be testing in real environment with them in real fires. This is another industrial project we are a lot of involved. It's Drone Hunter. So this drone is intended to be for protecting of airports, nuclear power plants, any critical infrastructure, or even privacy of rich people. So the drone is, in fact, the most of the clients are from this so far, because it's difficult to get permission of flying close to the airport. So far they are focused on these rich clients. So here you can see some video motivating this project. So let's say you have an airport to protect. So we did some tests in a military airport in Prague. There is a DJI Mavic coming. We have an external localization system which is detecting that drone, making an alert for the drone hunter. So the drone hunter is released autonomously from a box. Then it's not shooting anymore. Before, in the initial version, we were shooting a net, but there were a lot of disadvantages of shooting a net. So now the net is released from the drone. It's making this kind of, net to catch the drone. The advantage of this approach is that you can be flying even in windy conditions. With the shooting of net, if there is a slight wind from side, it will really affect your precision of shooting the net. You can have multiple attempts. So even you can catch multiple targets if your drone capacity is sufficient. And also, with shooting of net, you have much longer rope to carry the target, so you have bigger pendulum effect, which may destabilize the drone. So there are all the advantages of using this releasing net. There is another interesting application, but I don't know why the video stopped again. It's scanning. Yeah, so the task here is to use a swarm of drones or formation of drones, if you want, to localize a source of radiation. So the drones are equipped with onboard detectors of radiation, which provides information about the heading where the source of radiation is. So if you are moving, you can estimate the position. So as you can see in these pictures, the real source of radiation was hidden in one of these bins, or in one of the luggages in the second experiment. And the drone was, I will show it to you once more now, is able to, here is the visualization. So at the beginning, the position is not super precise, you see. So somewhere there is the source of radiation. So the red box will tell you this is my position estimate. Then you can use the ability of moving around to get more information and to localize the position more and more precisely. So you can then say, yes, this is in this bin. And the same with the with the other video. So they are using a Compton camera on board. It's a small detector, and they can achieve better results than using huge detectors that are transported by track, because with track you don't have the sufficient mobility. Usually the track is parked somewhere and then they start the detecting process, but with drone you can come closer to the source or to the estimated place of the source. So it's a big advantage. Another video, yes, I will use 7 minutes more to reduce our delay a little bit. In another video, I will show you the results of the Aerial Core project, which was already mentioned by Hannibal. My team is involved mainly in multi-robot system part of the project. So our task is to deploy several drones for inspection of the same tower in the same time, so a formation of multiple robots. Then some robots are even employed for cooperation, direct cooperation with humans climbing the tower. And also some drones are used for observing the humans and checking if they behave correctly. So we got like information from the partners, industrial partners from the projects, that even if they have a lot of safety regulations for the people climbing the tower, these guys don't follow the safety regulations and there is a lot of accidents just because of that. So this is a motivation to provide like information for the leader of the missions. So we did some research on the, now it's running, on the human following. So here you can see some initial simulations of a fleet of drones watching a human and circulating around him. Later on you will see the real experiments. Maybe I will move it a bit forward. So we are able to do a formation flying which is driven by the position of the human, and also the human by gestures can control the shape of the formation, the position of the formation. So here we are on the ground. Later on we will go to the tower. We also do some planning for long-range inspection. This was mentioned, even this paper was mentioned by Hannibal, so let me skip this. So this is just that we did some experiments, real experiments, later on even with real towers. We also, or my colleague Giuseppe Silano did some research on using signal temporal logic for planning the mission for multiple robots to be able to, again, to do inspection in a large environment. So multiple towers. Here you can see some simulations. But let's go to the real video. So this was done in cooperation with a local provider of electricity in Czech Republic. So they do the maintenance. Thank you. They do the maintenance of the power grid here, and they have to do regular inspections. So they are really motivated to replace their classical approach of using standard helicopters, human-piloted helicopters, with drones. So these pictures demonstrate the ability to control the drone by gestures, or even a formation of drones later on. The guy will be climbing the tower and the other drone will follow him. And then we have been also testing the long-range inspection with 3 drones flying around real towers. Maybe I can also skip this a little bit. Yeah, so this is a 3D model of the towers the drones are using, and here you can see some nice pictures of multiple drones flying around the towers. Okay, I guess this is the last project I'm going to show you. It's a pretty new research stream of my group. I like sea or ocean, so I wanted always to be a bit integrated into marine robotics. So we have found a project on coordination of and cooperation of boats and drones. So the motivation behind is delivering of cargo to ships, to real ships. So they want to they need to deliver some cargo, like package, let's say, and also usually grab some documents, for example, from the ship. Now, it takes time to get there by boat, it's expensive, it may be dangerous. So they want to replace it by drones. So the idea is to have fast boat, autonomous boat coming with a drone, and the drone will do the last mile delivery. And the second application we have is water surface monitoring and cleaning. We have even 2 projects on this topic. In the first one, we are interested in removing of objects like plastic bottles, as you can see here, from the surface of sea. Probably the most useful will be removing of fisherman's net, because like 50% of garbage in the oceans are these nets for fishermen, and this is something we can really localize by drones, and we can remove by boat. So the idea is to deploy heterogeneous team where the drones would act as eye for the drones, like, you know, this eagle eye providing you some information from above, and the autonomous boats will collect the garbage. Plus, we have a national project on scanning of lakes here in the country, because these lakes are affected by some diseases, mainly in summer, and if they are using it for fresh water, like drinkable water, they have to check regularly the quality of the water. They do it by cameras so far, but with drones you can go closer and again more precisely. Or they select some samples from water, so we will probably combine it with autonomous boat as well. Part of this project is also trying to remove the garbage by drones. We have found that if the garbage is light, like a plastic bottle, empty plastic bottle, and you are approaching it by drone, the airstream from the props is flowing the plastic bottle out, right? So it's really impossible to catch it by drone. But what we can do, we can hook for example, the nets. I don't know why it's not working, this video. So you can see that the drone is pulling some heavy object in the water. It's too heavy to grasp it, but it's possible by using force control to get it close to a boat, and the boat with manipulator can put this object out. So it's interesting research topic, because you have to design a force controller which is working under the condition of waves, water streams, and wind disturbances, and you have to also estimate the weight of the object to carry. So even you can check if you are able to take it directly, or you have to pull it, or it's too heavy for you before destabilizing you. So it's quite interesting research topic we are working on right now. And the last topic we are working on is landing on a boat in waves. So we want to be able to deploy the drones in really harsh conditions. So even if the wind and waves will be such big as you can see in this simulation, we should be able to land. So it's 10 times faster. So in real time, it's not so aggressive, but the drone is estimating the motion of the boat by observing the April tag, and then trying to predict the motion in future and applying model predictive control in a way that the drone is landing in the time when the boat is equal. So maybe at the end you will see that now, the boat was equal, so the drone landed. And we tested it also in real conditions using a real, like with oscillating, we used such a small boat. In fact, I am behind that boat doing the waves. And because we don't have sea, so we had to test it in these conditions. So the drone was waiting a little bit, trying to estimate the frequency of the waves. Of course, I was not super precise, so I didn't make super periodic motion. In a real ocean, it would be better. But still, the drone was able to estimate the motion of the boat and land. Yes, and later on you will see, maybe, hopefully. Excuse me? Yes, I know. Here, I wanted just to move it to save some time. So here we did some tests with autonomous catamaran, but it was not shaking, so it was super easy to land there, even if the catamaran was moving. Of course, we could manage the landing in multiple attempts. So if the boat is not shaking, it's pretty simple task. But if the boat is affected by the waves, it's complicated, as you can imagine. Okay, so thank you very much for listening and your attention. And we have still some minutes for questions.
Hello. Yeah, thank you for the presentation. I have one little question. It's more general question. Is it possible during the summer school visit laboratory or not?
Yes, yes, yes. There will be a lab tour. So in your program, you can see a lab tour. Do you remember which day? Thursday, probably. So you will be going to visit our lab, see the platforms. We will put there all the platforms we have for display for you. And also you will be visiting like other groups, for example, for the DARPA sub-T. You could see these docks, and like all these ground robots, for example. So there will be more than our lab only. But yes.
Thank you.
Yes. First, thank you so much for the presentation. Very insightful. I wanted to ask, in the few examples where you have a team of UAVs using model predictive control, what kind of concerns or things to consider would you say based on stuff like this modeling of the behavior of the other agents in the swarm? How can that affect the performance of a local model predictive control in a single agent? And also, have you considered stages where maybe it's a local knowledge that the agent has to perform their predictions instead of having, let's say, a central localization unit or something like that?
Okay. Yeah, thank you for this question. So in fact, we are usually using the model predictive control for controlling the single vehicle itself, and the effect of others around is just fitted into the cost function of the MPC, similar as other obstacles, for example. So this is one way how we use it, or even we use simple like Boyd's kind of, probably right, model, which gives you desired position or velocity, and this is entered as an input for the MPC. So it's kind of, there is a kind of cascade controllers. So there is a really low-level control plus then like middle-level control and high-level control. So for example, in the high-level control, there may be this swarming approach, and the second level is MPC, which is getting the commands from this higher level. We have also tried to integrate directly the plans of the others into the MPC, because for the MPC you can predict, or right, you have the horizon, prediction horizon, and you can estimate, or even you can know the horizon of others. So if you have communication, you can even communicate the prediction horizon of the other agents in the formation, for example, and then use this as an income for the cost function of the MPC. So, for example, this was used by Kratky sitting here. So hopefully I explained that correctly. So you may have several options how to play with the MPC. And the second question you mentioned was the global information, kind of. So as I said, usually we are not using the global information. Mainly, maybe only sometimes we use GPS if it's available, or like for the aerial core projects. Of course, if there will be no GPS, the drones will be not working, because we don't expect terrorist attacks during these experiments, for example. But in most of our research applications or agenda, we don't rely on any global information. So we usually rely on local information. Then, as I said, the robots are like kind of independent agents, so they will fly independently of others in their local frame, in their local map, and the others are used similarly as if we will be all going together for lunch now. You are also kind of observing the others, but you are working in your local frame. You don't care that you are in Prague, that you are in this building, because your task is just to get through the door with all the others around. So you have to observe the others, but behave locally. And you can do it without communication. Of course, sometimes you have to say sorry, or apologize, I have to go through, or something like that. But it would work even without communication, but maybe not so optimally. So if you play football also, if you can communicate, maybe you can behave better, but without communication, you will achieve the game as well. But we have also tested like limited communication. So I don't want, or I don't like sending all the map or everything, all the scans to all the other vehicles, because the scalability is not there for sure, never will be. But in some applications, you could send some few information. So for example, we were playing with the fact that if you are in the forest, you may use the other trees as your landmarks, let's say. So usually you can detect that there are trees around you. They are like stars, You see some stars constellation around you, and you can send this star constellation into other drones. The one that are close to you most probably will see part of your star constellation and can match this together. So you can estimate relative position by seeing the same star constellation from the two positions, like sailors do. So, and it's of course working much better, but you have to communicate, right? So it's always consent process. If you have more communication, more information, you will behave better, but you will be more affected by dropout of the communication. But thanks for the question. This one.
I think it will be the last one.
Oh, we can be delayed.
Hello, and thank you for the presentation.
Welcome.
It was really awesome to watch all of these. What I'm curious about this, like related to the radiation source localization problem. I don't know, maybe I can ask this later in detail, but how this Compton cameras work, and like, do you have directional information when you are trying to search for that?
So I'm not sure if I would be even able to describe you directly, like in detail. So definitely approach Tomas Baca, he's somewhere here, or Petr Stibinger. They are working this project. But roughly, yes. In some sensors, we have even the information about the direction. The sensor we have has multiple layers. So if there is an impact of the particle on the first layer, then it's detected in the other layers, and by the positions of the events, it works like an event camera. So the sensor. So it tells you, okay, there was an impact in the other layer, there was another impact. So you can track the particle, which was like a product of this impact, and based on that, you can estimate on the source of the particle, what was the type of the particle. By that you can also like distinguish between the natural noise and the source itself, and also you can estimate the direction of the source. But even without that information, if you have the intensity and if you are moving in a formation, for example, you can triangulate.
Okay, so the last part is also, like, I was also wondering how you advantage of being multiple instead of a single.
There is a big advantage if we are considering moving source. So if the source is static, you can measure, move, measure,
and map everything.
But if it's moving, you will measure, then move, but the source will move, so your triangulation will not work. And the task we are the most interested, mainly again, we always want to get there the multi, you know. So, so we told that guys, these defense guys, but in case your source of radiation is in a vehicle, you are not able to track it by normal methods as you are using. Use drones, you know, and team of drones, because if the team of drone will be static and your source will be moving, you can triangulate like in real time.
Thank you.
You're welcome. So maybe really last question, because I expect you are hungry. So if there is no more question, I will be here the whole week. So just
or maybe some online questions.
me.
Maybe we can.
Yeah, online. Okay, thank you.
Yeah.